Hello everyone, today in this video I will be discussing something about VHDL codes. Okay, now what is a VHDL code and how to write the VHDL codes which are being asked in exam, that we will be discussing in this video. Okay, now see, for each VHDL code we have two parts. The questions are asked from adders and subtractors and from the multiplexers, and for information, VHDL codes is in the module 4. Okay, now let's discuss how to write the VHDL code. Okay, see, every VHDL code has two parts, which is entity and architecture. Now what are these? We'll be understanding by using an example. Okay, now consider this example here. This you all know, these are the inputs A and B and C is the output, and this is the AND gate used. Okay, so these are the inputs and this is the output. Okay, for writing VHDL code you need to know what are the inputs and what are the outputs. Okay, so the inputs are A and B, output is C. First mention this. Okay, that's the entity part. Inside the entity you will mention that and the architecture part will be what is the equation of this. Okay, see here, this is the AND gate, right? AND gate means these are the inputs and this will be AND, and the output is C. So C is equal to A and B. That's the equation. The equation will be mentioned in the architecture part. Now let's see the syntax for the VHDL code. See, you'll start from here, entity AND gate. You can mention any name here, then is. So entity AND gate is, inside this port you will write this. Okay, see, inside this bracket you will write this, what are the inputs and outputs. You will write A comma B in bit and C out bit. That's the inputs and outputs which you have mentioned inside the port. Then you will write AND gate. Okay, that's it. That's the entity part. Now coming to architecture part, you will have architecture sum. You can give any name here of AND gate, which for which entity you are specifying the architecture, that name you will write here. Okay, so entity AND gate I will write here is. Then you will write begin and end. In between begin and end you will write the equation. The equation will be written in this form. C is the output, so this one, this arrow, less than or equal to. Okay, that is used for the equal to sign. Instead of equal to sign in VHDL code we will write in this way. Then A and B, that's the equation, right? A and B are the inputs and C is the output. In architecture you will be mentioning that. Now after knowing about the basic part, let's see what type of questions are asked in exam. Okay, first part is from adders and subtractors. The question will be of this type. Write the VHDL code for half adder. Okay, now for half adder you need to know first what are the equations for sum and carry. Okay, for sum it is A XOR B and carry it is A and B. Okay, after knowing this you will write these two parts, which is the constant for all the VHDL parts, library IEEE, then semicolon, use IEEE dot std logic underscore 1164.all. that is including the header file. Okay, like in the coding also we write the header files, right? So we are including the library for this VHDL code. Then coming to the writing part, coding part, you will have the entity and architecture. Okay, every VHDL code will have two parts, which is entity and architecture. In entity you will write the inputs and the outputs. See here, what are the inputs here? A and B are the inputs, right? So you will write A, B in. Instead of bit you will write std logic. Okay, then sum and carry I am denoting as SNC out std logic. Okay, that's the input and output which you will be mentioning in the entity part. Then and the half adder, the entity name will be what VHDL code you are writing for. Okay, half adder. Then end half adder will end the entity part. Then coming to the architecture part, you will have architecture gates of half adder. You can give any name here, and which entity you are mentioning, that should be the same thing. Okay, half adder. You have used here half adder, then mention that same here, half adder. Okay, then in architecture part you will have begin and end. In between that you will write the equation, which is for sum and carry. Sum is equal to A XOR B, carry is equal to A and B. Okay, that's the VHDL code for half adder. Now for full adder also it's the same thing, but there is a slight bit difference, which will be signal and the component will be used. Let's see what it is. First write the equation, sum is equal to A XOR B XOR C, carry is equal to AB BC plus CA. Okay, now after simplifying this you can write it in this form as well, AB plus C into A XOR B. Okay, that's the another version of carry. Okay, AB plus C into A XOR B. For all the codes you will write this first, then after that entity part and the architecture part. Inside the entity part the ABC are the inputs in std logic, sum and C out std logic. Okay, then end full adder. Then in architecture part you will have this component. What is this component? See, the question is in this form, write a VHDL code for full adder using half adder as a component. As you know, full adder is the combination of two half adder, right? So we'll be using this half adder as a component for constructing this full adder. Okay. Now let's see the component part. See, the component part is same, just instead of entity you will write this component here. The same thing for half adder which you had written, right? See here, this same thing, this same code you will copy and write in the full adder, just instead of entity you will write there as component. Okay, that's it. Okay, instead of entity you will write here as component. Then after doing that, signal you will use. Why we use signal? Let's see now. For signal I will be giving you a small example. See here, suppose that A and B are the inputs, and this is an AND gate which is connected to another AND gate here. Okay, this is the AND gate C and D. Okay, now here is the final output Y. Okay, now for this here also you will get some value, here also you will get some value. That values will be input in the Y. Okay, so the starting part is the input, this is the output. The intermediate values which you get are known as signal. Okay, so we are specifying the signal in this way. So this I can take as P, this I can take as Q. So the Y equation will be P and Q. Okay, all right. Now moving on, after knowing that, we'll have these signals here. Some of the first gate, carry of the first gate, this is the carry of the second gate. Okay, then we'll be writing here colon and bit. It has no input and output, so it will be written as bit. Now after specifying signal, we'll do it as same, begin and end we'll write. In this we are using two half adders, right? So half adder 1, half adder 2. Inside that we'll write half adder, and then port map is the calling of that. By using port map we will be calling this half adder. Okay, and we will put in the inputs which is A and B. This is outputs S1 and C1. Then inside the second port map you will write S1 and C in, then sum and C2 are the outputs. Okay, how you will know what to write here, that will depend on the circuit diagram. Okay, in the circuit diagram of half adder, the first half adder has these inputs and these outputs, and the second half adder have this inputs and these outputs. So we have written in this form. Now after getting this C1 and C2, finally in the full adder circuit you will have this OR gate here. Okay, OR gate will be C1 or C2. Okay, two half adders, carry will come input side of OR gate, and the output will be the final answer of C out. Okay, AND gates after that. That's the entity for full adder. Now moving on, the half subtractor and full subtractor is also same, just the equations will vary, and according to that you will make the changes here. Okay, for example, this borrow is in this way, right? It's for carry it was A and B, right? For borrow it is not A and B, so you'll write here not A and B. That's the only difference. And for full subtractor it's same thing, and equations will get differed accordingly. Okay, that you will write here, and you will use difference and B out. B out means borrow out, B in means borrow in. Okay, now by using that you will write the equations, all are same. Instead of S1 you will write D1, instead of C1 you will write B1. Okay, B2, B in instead of C in. That's the only difference. At last you will write B out less than or equal to B1 or B2. Okay, now if they ask you about the 4-bit adder, what you have to write is you will use 4 full adders. Okay, for adding 4 bits, and see the inputs and the outputs. See how to know what are the inputs and the outputs. See here, which arrow is coming in, Ci, A0 and B0, these are the arrows which is coming in, that are the inputs. Okay, and the outputs are S0 and C1 which are going out. Okay, so these two are the outputs, these three are the inputs. That we will be mentioning in the entity part. First we will write the entity part. Inside the entity part we will write port, then AB are the in bit. Okay, now why we have used vector. See here, if you use multiple inputs, that will be used as a vector. Okay, 3 down to 0, 3 down to 0 means from B3 it's B0, right? Similarly for A3 to A0, right? So 3 down to 0, and Ci is the in bit because only one Ci is coming, so it's the in bit. Then similarly for the S out also, S out bit vector 3 down to 0, that is S0 to S3, right? 3 down to 0, so 3 down to 0 for S out also, it's a vector. Then CO is the output, which is the final output which we get here, that is CO, that's the out bit. Then we will write AND adder 4. Inside the architecture you are using the component full adder, right? See, we are using 4 full adders. that's represented by f0, f1, f2 and f3. Okay, 4 full adder as a component. So we will be writing the component full adder as what are the inputs for the full adder, output of the full adder and n component. After that, signal C. Why we are using signal C? See here, 3 down to 1. Let's see what it is. This one, C1 to C3. From 3 to 1 we are using 3 inputs, right? Signal in between. See, this is the output, this is the input, and these are the intermediate parts which will be used as a signal. So we are writing C3, C2 and C1. After knowing that, we are using the begin keyword for writing the VHDL code. Inside the architecture part we will write FA0, FA1, FA2, FA3. That's the full adder. We'll be using port map to call the component full adder, and we'll be passing the inputs. Let's consider the first example here. See here, A0 and B0 are the inputs, Ci is the input. So A0, B0 and Ci are the inputs, and C1 is the output, S0 is the output. Considering this diagram here, you will have the A0 and B0 here, Ci is the input, SO is the sum of this full adder, and C1 is the output of this carry, right? So S0 is there and C1 is there. So we are mentioning that S0 and C1 here. This is S0 and C1 here, and Ci, A0, B0, that is the values of these. Okay, A0, B0 and Ci. Okay, so that was for FA0. That's the first full adder. For the second full adder, we'll use the same thing, A1, B1, then C1, then C2 here and S1 here. Okay, so in the second line we'll write this accordingly. What are the numbers for each full adder, that we will be mentioning here. After doing for 4 full adders, then we'll end the structure here, which ends the VHDL code for 4-bit adder. Coming to the multiplexer part, there are 2 types of questions which can be asked under the multiplexer, which is write a VHDL code for 2:1 multiplexer, which is very straightforward. First you have to construct this 2:1 multiplexer diagram. Okay, now what is a multiplexer actually? See here, these are the inputs. Okay, D0 and D1. This is the output. Now if I have to select between D0 and D1, how will I specify? I will be specifying using A. Okay, if A is 0, D0 will be selected. If A is 1, D1 will be selected. Okay, in that way I will specify D0 or D1 should be selected. Which one will be selected, that will go to Y. Okay, now for that also we'll write these 2 lines. After that we'll specify the entity. Inside the entity you will have the inputs and the outputs. See here, observe, these are the inputs, and A is also an input because it's getting considered for the selection of this or this. Okay, so these 3 are the inputs and Y is the output. So inside that we'll write here port D0, D1 and A as the input, Y is the output. Then we'll end multiplexer entity. Then we'll write the architecture, which is the architecture behavioral of mux 2:1 is begin and end. Between the begin and end we'll write Y is equal to not A and D naught. Now see, observe here carefully. When A is 0, we are using D naught. So A is 0 means not A. If A is 1, it is A and D1, not A and D naught. So in that way we will make the equation and write in the architecture part. Okay, so not A and D0, when it is 0, D0 should be selected. When A is 1, D1 should be selected. So in that way we will write the Y equation using an OR. Okay, that's the architecture part for 2:1 mux. The second type of question which can be asked is design a 4:1 mux using 3 2:1 mux. Okay, so this is the 4:1 mux. These are the inputs. Inputs are I0, I1, I2 and I3. B and A is also the input. Okay, and we are using 3 multiplexers and the output is Y. Now we have to write the 2 equations. Now see, this is the component here. See, by using 2:1 mux, so we will use this 2:1 mux as a component. Okay, now after making this diagram, we will move on to the equation. See, expression for 2:1 mux, A bar I naught plus A I1. This is the same thing here. See, A bar Y, if it is 0, I0 should be selected, right? If A is 0, I0 should be selected. If A is 1, then I1 should be selected, right? So A bar I naught plus A I1, that's the equation for 2:1 mux. Similarly for 4:1 mux, we will have 4 values, which is A bar B bar, A bar B, AB bar and AB. Okay, now let's see by using a truth table. Now see, observe here carefully, we will have AB and I here. Now when A, B both are 0, I0 should be selected. When A is 0 and B is 1, I1 should be selected. Similarly, I2 and I3 will be selected based on the values of A and B. Okay, what is A0 and B0? That's A bar and B bar. If it is A bar and B bar, I0 should be selected. So see here the equation part. Before that, the entity part is the same thing. We will use the component. First we will specify the entity mux 2 to 1, then we will use the architecture for this, the 2 to 1. That's the same thing. We are writing the same thing which we had written before. Then after doing that, we will move on with the 4:1 mux part. Okay, in 4:1 mux you have the inputs AB, I0 to I3. Okay, and Y is the output. This is the 4:1 mux. Inside this, A and B are the inputs. I0 to I3 is I0 to I3 are also the inputs. Okay, only Y is the output. So we will be mentioning that in the entity part of 4:1 mux. Okay, so A, B, I0, I1, I2 and I3 are the inputs. Y is the output. Okay, after doing that, we'll end the entity part. Then we'll begin with the architecture part. See, we are using mux 2 to 1 as a component, right? See here, mux 2 to 1 is used as a component. So we'll be specifying that. We'll write here the inputs and the outputs of mux 2 to 1, just same as this one. Here what we had written, the same thing, only instead of entity we will write the component. After doing that, we'll use the signal P and Q. See here, observe here, we have the inputs here, we have the output here, but in between we have two more connections which will be represented by signal. The signals used are P and Q. This is for P, this is for Q. Okay, now after specifying what are the signals, we'll begin the architecture part and end here, and in between we will write M1, M2 and M3. Now what are M1, M2 and M3? See here, three multiplexers are used. This is M1, this is M2, this is M3. Okay, so M1, what are the inputs? I0, I1 and B, and output is P. Okay, so we will be specifying that here. We will be calling this component and specifying the inputs B, I0, I1 and P. Similarly for M2 also, B, I2, I3 and Q. And M3, what is M3 here? See, inside the M3 you will have two signals here, P and Q as the input, and A is the input, Y is the output. So A, P, Q are the inputs, Y is the output. A, P, Q and Y. So we will be calling the 2:1 mux by using these inputs and the output, and that ends the multiplexer part for this 4:1 mux using three 2:1 muxes.